I think this week material is a little bit abstract for you, like maybe a little abstracter than last week material. And the reason why is that is because you have not seen the application of these notions. Maybe I'll have give you some intuition about these definitions. First, I would need some experience about calculus. All right. When you talk about open sets, the intuition is something. What do we mean by this? Like, given that you know the open balls are open, right? You have seen that the video or on the notes. You know that open sets or open balls are open. We use that. The thing is that, like, when we talk about in your calculus, we define this, right? What do we mean by this? We mean by for absolute bigger than 0, there exists delta. There exists delta bigger than 0, and if x prime minus x. Less than delta, then f of x prime minus f of x. That's an absolute. Right, you have seen this in your calculus course. So with this kind of open balls, they're actually writing that x prime in and delta x, then f of x prime in and epsilon f of x. Right, it means something like very near. We try to use this kind of like near to define something like continuity, define something like limits. We're saying that if it's near in this way, like the distance is less than delta, then we do this. And actually, this definition, I'm not going to prove that here, but we can see that we can rewrite it in this way. For all open sets U that contains f of x open, then there exists V open if x prime in V, then x in V. So it's like this determines some open sets here, and this one determines some open set here. So we have like this kind of definition. This one is dependent on we'll see that like maybe 3 weeks later. But you have this kind of notion that openness about something like neighborhood is very near, is like a distance small, something like that. We're doing that thing. And a closed set. Okay, so the open set, we'll just give a definition. Definition is, if I say U is open, I mean for X in U exists R larger than 0 such that N R X those things. So we have similar notion about closed sets. So what we need closed sets? Because we need something like, I want the limit lies in the closed set. So the topology is actually not about the sets. The sets is about like how would the sequence and the functions on those sets be like. So when we're talking about like closed sets, we're saying that, okay, so every converged sequence, the limit lies in the set as well. That is the way we see topology. We're not talking about the set itself, but we're talking about the behavior of the sequence and the function on that set. So it seems like a little bit abstract to you because you haven't seen any sequences and functions on those sets. Okay, so the intuition is I want if an is in F that is closed, then limit and converge. I want limit an to something else.
Does this definition include the empty set?
This is the I'll go through that later. So you're seeing that. I think you do it this way. Like all the midpoints lies in F. And you can think about like, how does what is this definition? I mean by if all limit points in F and every sequence, every converged sequence has limit in F. Right, so definition is like all limit of F is closed and only if all limit points of F lies in F. And these are the potential guys that may be some limit of the sequence in F. So we're thinking about like if G is the limit point, find a point here, and then a point maybe here, and then a point maybe here. Because like for all delta, what do I mean? Oh, I mean like for all delta within 0, there exists some we're doing this, we can pick a point here if we do this ball. We can pick a point here if you do this ball. And we pick a point here if you do this ball. So in that way, this point is a limit of the sequence. Is that okay for you? After going through this, this kind of definition, like it regulates the behavior of the sequence. But since we're talking about the set itself, so maybe we turn back to this kind of definition and forget about those sequence. That's more like convenient when you're doing those operations. When we're saying that something's open, something's closed, you have to keep this in mind, that we're not regulating the set itself, but the behavior of the sequence and functions. Some examples of open and closed sets. So the first one, the open ball is open. Sorry, not the end. I should introduce this one. Just like a little remark. If you read other books, like not rooting, you'll see like a lot of different notions. You see, I say this kind of as I say it's just NRX. I think they call it neighborhood, right? But I call it open ball, or I think the video also call it open ball. And this guy, you sometimes see it in this way, like ball. And you sometimes see it in this way, or this way. Or I think I have seen this way, and this one is announced. So it's just the same thing. So if you see someone write this, it's not wrong. It's just like use different notation as yours. Introduce this one.
Don't confuse me.
I'm not confusing. If you see, if you're like, I use like B so much, and if I just like misuse it as if B, just like don't correct me, you know that it's M. Open. So you're thinking that we're doing this. This one mind R. And to pick some points, you want to set a ball here so that this one is open, right? You can prove that this one is open. You want to do this. At every point here, you can construct an open ball. So you're asking that what the radius here should be. And you do not want it to big, too big, so that it will be this. This one is too big. So at most you can do is this. The largest you can do is this. Right? You just touch here. So it seems like if I pick something, like I call this R, it seems like R prime here, I just do that R prime equals to R minus F dx. If I do this, I'm safe because of this. Seeing this graph, here's R, here's R, here's R prime. So here's dx x prime. So R prime here should be this one minus this one. It would just do that. Okay. For all, take for all x prime in n or x, we take R prime equals to R minus dx x prime. So we're trying to prove, we want to show that n R prime x prime still being n or x. And by definition, what do I mean by this term? I mean for all x prime. In n R prime x prime. That's this one should be for all x prime with d for x prime with d x prime x prime lower than R prime. I want d x prime x lower than R. Right, it's by definition. What's this set? I collect all points. The distance is lower than R prime to x prime. And this one is the distance to x is lower than R. So what do I mean by this subset? I mean, if your distance x prime is lower than R prime, then your distance to x is lower than R. Okay? So what do I mean is if this one is 1 being by this one is x prime in n R prime x, and this one is x prime in n R x. Cool. You can see this one, dx prime x is lower or equal to dx prime x prime plus dx prime x. And this one, this one is lower than R. This one is lower than R. So you know that it's lower than R plus dx prime x. R prime. So this one is lower than R prime plus D. Lower than R prime plus this one. Lower than R prime plus this one. So close to R. Just watch this graph, see this graph, and you can know what I'm writing. That if there one is x prime from here, then the distance here, I want to say that this distance is lower than R. And because this plus this is lower than R, so this one's lower than R. And why this one plus this one's lower than R is because this one is less than this one. Cool? Second. It's open and closed. So this one is a little bit tricky. It's just like it brings like no sense, but it's just a logical exercise. So it's just induced by purely mathematical logic, but not intuition. All right. We're open. I say U is open. What do I mean? I mean, for all x in U, there exists R greater than 0, blah, 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 blah. Right? I'll write that. And Rx U. So what do I mean by U? It's not open. What do I mean by U is not open? It's not open means that I need to negate this position. So I mean, like there exists some x in U for all R greater than 0, and or x is not in U. All right, these are definitions. And compare this, okay, if phi is not open, then there exists some point in phi, blah, 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 blah. But there's no point here, so it cannot be not open, so it must be open. Is everything clear? It's a logical exercise, because if it is not open, then there exists some point in here, satisfy something. But there's no point, so it cannot be not open, it must be open. Similar for closed. What's the definition of closed? That all limit points of f is in F, right? So what do I mean by it is not closed? I mean, there exists some limit point of this set that is not lysing this set, but it has no limit point. So it cannot be not closed. So it must be closed. Cool? Cool? Cool.
That's cheap.
Yeah, that is. Let me check what should I go to. Let me check. So position. I'll do what? I'll do the finite. Okay, I'll do this one. Finite intersection of open sets is open. And union of open set is open. Blah 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 blah. I'll prove only the first one. And you should do the second one. How to prove this? So writing down like, okay, let's say UI, I think there's a thing that the video didn't say much about it, that if we say something is open, like if we something like variables, we usually use X, right, X, Y, Z. When something like coefficient, we use A, B, C. And we're talking about open sets, we usually use U. And closed set usually is F. This UI open. And we're trying to say that, okay, what do I mean by for there are n sets? What do I mean by they are open? I mean, for all x in UI, there exists some r greater than 0, such that n Rx lies in UI. But to make it like more clear, I'll do this. I call it Rix. I want to show that I n is open. What do I need to show is that for all x in n UI, there exists some r greater than 0 and Rx here. And UI. Oh, so again, the graph. Now here's some points. It do this one, it lies in this one, and he do this one, it lies in this one. If he do again this one, it lies in this one. So which one you should pick? You should pick the smallest, so that it can lies in this. If we pick the smallest, it drops into the intersection. Can you understand this graph? Yes? So the strategy is, so peak R equals to the minimum of Rix I. And we know n Rx lies in n Rix
x lies in uy or y, which means that n of x
So the second proposition. Should I go through that one? Okay, I'll go through. Oh, sorry. Before this proposition, I think I have more things to say. That's remark. Some intersections of open sets is not open. And the reason why is that is because that the minimum, like it can just disappear. There's no minimum, or minimum is 0. That's minimum is 0, the infimum is 0. So the example would be something like negative n 1 over n over. This one equals to 0. Because of like this, for 0, the Rix here is 1 over n. So you should pick R equals to 0. But we want R is greater than 0. So that's boom. It's okay, maybe like it's the set. It's a set. If it's not open, then it must be closed. It's the proposition, right? Something's open and it must be closed. If you think that's right, raise your hand. If you think it's not right, raise your hand. Alright, cool. So you understand that one. It's the open and closed is somehow confusing. So there is like the set here is open and closed. It goes open and closed. There's some set that is not open and not closed. Okay, cool. The position of U is open. UC is closed. So try to imagine the thing. The open, it seems like we're trying to do something like this, right? This one is open, like something without boundary. And closed is something like this, closed. It's something with boundary. So it seems like the open set, the complement of open set, should contain the boundary. So it must be closed. The intuition is like that. this, you're proving it's just saying that, okay, anything here is not a limit point. You're done. Right. Anything here is not, I'll just sketch the proof. Sketch. So if X in U, then you can draw an open bowl here. And if you can draw open bowl here, which means that it is not a limit point of the complement. Right? It's not the limit point of the complement. So it does not contain so all the because anything here is not the limit point of the complement. So all the complements, so all the limit point of the complement cannot be in this sense. So all the limit points, let's see the complement itself. No. And the reason why I'm not writing it down is because. Okay, cool. Another notion is the closure. This one is a little bit complicated. That I think maybe I'll give you like more materials about that, and I will not test on this time. But if you have any questions about this one, you can ask me or the TAs in the spring break. And not only about this, but also the interior. So maybe I'll provide some materials, like maybe these 2 days for you to read or to learn about it. Cool. Yeah. Any question? No? Yeah, like what say what set is open, what set is closed. Yeah, like thinking about this thing. Let's say maybe. Have you learned about something like uniformly convergence thing in your calculus course? I'm not so sure. No. Don't think about thinking about.
Do they remember?
I'm not sure if they go through it. So you don't have not learned uniformly convergence. That's possible.
I think it's in the syllabus.
Uniformly convergence.
Yeah.
So if you have learned that notion, then you know that the uniformly convergence, you can think that you can define a metric on the continuous continuous function. And what there's a theorem called that a sequence of continuous function is uniformly converged and the limit is continuous. So I mean that in that metric space, the continuous function set is closed. Actually, I mean in the topological way. Cool.
Okay, so there is a limit of the function, but I'm not sure if there is discussion of whether the limit is continuous. That's the first point.
I think the course ends here. 停止录，还在录。关掉吗？关掉，关掉，关掉。